So here it is, the mini lecture you've all been waiting for, Mass Spec, or it's not voodoo, really. Okay, so the mass spectrometer is a very interesting instrument, and more than other instruments, I'd say it's really valuable to look at the details in the book, so you can kind of get a better idea of what's happening inside that black box. So that's up to you, but I will highlight the major features by saying you take your molecule, you put it into the mass spectrometer, and kablammy, it is blown into pieces. You're hitting it with a beam of 70 electron volts of electrons. An electron beam, this amounts to almost 7,000 kilojoules per mole. What happens? It knocks an electron out of that molecule. Because an electron is negligible in terms of the mass of the total molecule, that's going to tell you the molecular weight of your sample, which is probably the most handy piece of information you'll get out of a mass spectrum. But as you can imagine, you just knocked an electron out of a bond or a lone pair somewhere. Yikes. Then, what happens next? Well, you've probably played Jenga or a game like it, and you probably know that at some point when you get pretty far along and you try to remove one of these pieces, it all falls apart and you don't have your structure anymore. You have all these little fragments. Same sort of thing in mass spec, it's just that the little fragments aren't all the same. So this is what you get. This is the record of the data in a mass spectrum. So let's look it over. First of all, the x-axis is mass to charge ratio. Well, the charge is 99.9% of the time 1. It's just a single cation. So you can pretty much just x out, come on pen, x out that and just read the mass directly from the x-axis. So all these signals here are pointing out signals of, for example, this one right here has a mass of 50 atomic mass units. Alright, what about the y-axis? Well, that is how much, relatively speaking, of each of these pieces amounts to in your sample. So it blows apart into pieces, but some pieces are more prevalent than others. For example, this piece at 91, there's quite a bit of it. In fact, it's the most formed. We'll see that that has a special name. So the relative abundance is on the y-axis. The peak that tells you what the molecular weight of your sample is called the molecular ion. It's the biggest one, furthest to the right, sort of. Often it's a little fudgy, and we'll talk about that. And then, as I said earlier, this peak that is more abundant than any other, it is arbitrarily set to a relative abundance of 100%, and therefore everything else is relative to it. That's the base peak. It's basically, haha, no pun intended, the fragment that is formed in the greatest abundance because it's the most stable. So that's kind of a take-home message. Anything that shows up in the mass spectrum, it shows up because it's stable enough to follow the flight path all the way from the sample injection point to the detector. Otherwise, it crashes and burns along the way, and it doesn't show up. Alright, what is my philosophy about mass spec? It is voodoo, unless you use mechanism to predict the patterns that you will see in a mass spectrum. But that's in chapter 2 stuff. It's introduced in chapter 16 without the mechanism at all. And so I just want to give you an example of how useful it is going to be to understand in a mechanistic sense what is going on. So I take hexanes, blast it to pieces with this 70 electron volt electron beam, and I lose an electron. We indicate that loss of an electron by this symbolism. If I lost an electron, that's a -1, so it's now a cation, and obviously lone pairs, bonds, whatever, are two paired electrons. So if I smack one out of the molecule, I'm going to have one unpaired electron. So this is a symbolism of my molecular ion, often abbreviated M plus dot. So that's the molecular ion. And again, whatever the molecular weight of hexanes is, this molecular ion will have the same molecular weight because the mass of an electron is so infinitesimally small. We don't know where the electron came from, but we can guess. Let's guess that it came out of that bond right there. Now that's an arbitrary guess. We'll get a lot more rational about it when we get to inner chapter 2. If indeed that is where, is that 1, 2, 3, 4, 5, 6. If indeed that is where the electron got bopped out of, you can imagine now that, holy cow, this bond is pretty much not a bond anymore. So this guy will fall apart in a heartbeat. And there's no electrons to move here, so we don't even have an arrow. But this falls apart in a heartbeat to give me a methyl radical, which is neutral, and our 5-carbon cation. So I got CH2, CH2, H2, H2, H3. Well, that's 5 times 12 equals 60. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 hydrogens. I would expect to see in my mass spectrum a signal at mass to charge 71 indicating that this cation was formed. So that's kind of the overview of what's going on in the mass spectrum. Two important things to note. Only charged species are detected. So if it's just a plain old neutral radical, it goes out into the atmosphere, is not detected at the detector, doesn't show up in the spectrum. And just like IR, we're going to ignore probably as many as 95% of the peaks in the mass spectrum. In fact, in some mass spectra, the only thing you're going to get out of it is the molecular weight. So don't try to analyze everything. Nope, the key information that you'll get out of a mass spectrum is the molecular ion, which tells you the molecular weight. The fragment ions, that's, like I said, we'll be talking about that within chapter 2. That can give us some important structural information. And the isotope peaks. So, molecular ion. The trick with the molecular ion is that it's not always real obvious which one it is. If we can figure it out, then yeah, it's really great because it tells us the molecular weight of the sample, which is something that neither IR nor NMR can do at all. Better yet, if it's an odd molecular ion, say 71, now this is for the molecular ion, this is for M plus dot. Alright, M plus dot. It hasn't fallen apart yet, it just lost one lousy electron. An odd molecular weight is most likely containing a nitrogen, a single nitrogen, or maybe 3 nitrogens, or maybe 5 nitrogens. In other words, an odd number of nitrogens, because nitrogen will give an odd molecular weight. It's called the nitrogen rule. And that's, you know, fairly reliable. But, like I said, it's not always really obvious which one's the molecular ion. So here's a piece of that molecular mass spectrum. And what you look at is, of course, the cluster of peaks at the highest molecular weight. Because anything to the left is a fragment ion, something that's fallen apart from your initial sample? Well, there's a lot of little signals there. Which one of these, this guy, there's even a little teeny guy right there. Which one's a molecular ion? You know, it would seem to stand to reason that the highest molecular weight would be your molecular ion, and that reason would be incorrect because those are isotope peaks, which we'll talk about in a minute. So, in a very unsatisfactory definition, the molecular ion peak is that guy that's kind of the largest peak furthest to the right in the mass spectrum that has the little tiny M+1 and M+2 isotope peaks to the right. But, yikes, sometimes the molecular ion peak doesn't even show up. And that is because when you have a molecule that falls apart so easily that that molecular ion peak can't reach the detector, it won't be detected. So here's a great example of that. This 2,2,4-trimethylpentane, molecular weight is 114, ain't nothing at 114. The molecular ion peak fell apart immediately to give you a base peak at 57. So, if you didn't know this was 2,2,4-trimethylpentane, you would probably think, well, I'll bet you any money that's my molecular ion peak, and guess what? Unfortunately, you would be wrong. Alright, well, what about these fragment ions? Well, believe it or not, there is some rationality to how these things fall apart, and we'll see that in Inner Chapter 2, which will be coming up in the next mini-lecture. Important note, the fragmentation stuff will not be on Exam 1. The other key information, isotope peaks, however, will be, because that's covered in Chapter 16. So isotope peaks, these little M+1 and M+2 peaks, can be used to determine exactly what the molecular formula was, which is really handy. Because say you figure out the molecular weight is 200, well, there's a bazillion different molecules with the molecular weight of 200, but what's the molecular formula? So Mass Spec can come in very handy there. And there's a special application of isotope peaks that really helps you nail down halides. So, what's the deal with these isotope peaks? Well, it's a simple fact that molecules are made up of all kinds of atoms, and atoms exist as isotopes. You know, we're in organic chemistry, so 99% of the time, 99% of our samples are going to have C12 in them. But they also have a small proportion of C13. There's a teeny tiny amount of deuterium in each sample. A negligible amount, but it's there. If there's oxygen in my sample, well, you know the regular isotope for oxygen is, the most abundant one is oxygen 16. But there's oxygen 17, oxygen 18, nitrogen 15, etc., etc. So, it should be clear that this guy, and this guy, and this guy, and this guy, for example, would contribute to an M+1 isotope peak. This guy to an M+2 isotope peak. And anything beyond that is astronomically, vanishingly small. So we will always have M+1 and M+2 isotope peaks. Now, back to our little sample mass spectrum. So we pointed this out before. Now we know that what this guy amounts to is the presence of some C13 in my molecule, trace deuterium in my molecule. If this is oxygen containing, maybe some O17, etc., etc. All those little amounts of isotopes add up to M+1. And then if this is, you know, has some oxygen in it, this would be from the O18 present. So that's the story with the isotope peaks. There they are. So now we know that's the molecular ion, and those little guys are the isotope peaks. The nice part about the isotope peaks is that you can conveniently estimate the molecular formula by comparing the intensity of this M+1 peak to the molecular ion peak. It's a very handy thing to be able to do. It's something you would have to do on homework. It's not something you will have to do on an exam. But you should get the general gist of it, and the book covers it in good gory detail. Now, the really nice feature of isotope peaks is that it lets you absolutely nail down the presence of bromine and chlorine. Bromine has two isotopes, 79 and 81, and chlorine, 35 and 37. The ratio of bromine 79 to 81 is almost 1 to 1, and 35 to 37 is, I think, something like 2 to 1 or 3 to 1. So, if you see, holy cow, two peaks that are almost exactly the same intensity, that are M plus 2 AMU apart, then this is, yes, screaming bromine. If down here on the fragment ions, I saw, oh, right there, looky there. See how those two little peaks are almost exactly the same intensity and they're 2 mass units apart? Whatever this is, that fragment ion contains bromine. Okay? So that's the dead giveaway for the presence of bromine in your molecule. For chlorine, you'll see the same sort of thing. Oof. That's supposed to be a straight line. This is supposed to be 2 AMU apart. But this will be due to the presence of chlorine 35. And this guy will be due to the presence of chlorine 37. So your M plus 2 peaks otherwise are never that intense. It's just that you have such large abundances of the M plus 2 isotope for chlorine and bromine that you can use it in Mass Spec in this way. So there you go. Alright, wrapping it up. I thought this was the best Mass Spec cartoon I could find. It's a little odd. You gotta admit that scientists have kind of a warped sense of humor sometimes. Maybe. Okay, that'll do it for this mini lecture, and we will see you in class where we will fragment or something like that.